Imagine waking up tomorrow to discover that a single rock floating in space contains more platinum than has ever been mined on Earth. Not a fantasy, but reality. Right now, as you watch this video, there are asteroids drifting through our solar system carrying enough precious metals to crash global markets overnight, enough rare earth elements to power our technology for millennia, and enough water to fuel humanity's expansion into the cosmos. But here's what will shock you even more. We're not just dreaming about mining these cosmic treasure chests anymore. Companies are already building the technology, nations are writing the laws, and the first asteroid mining operations could begin within the next decade. What you're about to learn will fundamentally change how you think about scarcity, wealth, and humanity's future among the stars. Before we dive into this cosmic gold rush, I want you to do something for me. Drop a comment right now telling me where in the world you're watching from and what time it is there. Are you in Tokyo at midnight scrolling through your phone? Maybe it's morning in London and you're having coffee? Or perhaps you're in Los Angeles watching the sunset? I love connecting with viewers across the globe, and it helps me understand when and where people are most curious about the future we're building together. Now let me paint you a picture that should terrify every world leader, every economist, and every person who uses a smartphone. We're running out of stuff. Not food, not water, not oil, though those are concerns too, but the building blocks of modern civilization itself. The rare metals that make your phone vibrate, the elements that create the magnets in wind turbines, the platinum that powers fuel cells, the lithium that stores energy in batteries. We're consuming these materials at a rate that would make our ancestors' heads spin. Consider this sobering reality. Humanity now extracts over 100 billion tons of materials from Earth every year. That's roughly equivalent to mining and moving a mountain the size of Mount Everest every single month. The rare earth elements alone, those mysterious metals with names like neodymium, dysprosium, and terbium that most people can't even pronounce, are projected to see demand increase by 300 to 500% over the next 2 decades. But here's where it gets truly frightening. China controls about 90% of the world's rare earth production. What happens when geopolitical tensions rise? What happens when these mines run dry? What happens when the environmental cost of digging deeper, processing lower-grade ore, and destroying more ecosystems becomes unbearable? The electronics in your pocket require dozens of different rare metals. Your electric car needs lithium, cobalt, nickel, and rare earth elements for its batteries and motors. The solar panels that might power your home depend on silver, tellurium, and indium. Wind turbines need massive amounts of rare earth magnets. We've built our entire green energy transition on materials that are becoming increasingly scarce and environmentally devastating to extract. Traditional mining operations leave behind a trail of destruction that's almost incomprehensible. Copper mining creates approximately 99 tons of waste for every ton of copper extracted. Gold mining can generate up to 20 tons of waste rock for every ounce of gold. The rare earth mining operations that power our high-tech world create radioactive waste ponds so toxic they can be seen from space. Meanwhile, our demand continues to explode exponentially. The International Energy Agency projects that the world will need 42 times more lithium, 25 times more cobalt, and 7 times more rare earth elements by 2040 than we used in 2020. This isn't gradual growth. This is a resource tsunami heading straight for a supply chain that's already showing cracks. Some experts call it the Great Acceleration. Humanity's resource consumption has increased more in the last 50 years than in all of previous human history combined. We're not just approaching limits, we're smashing through them at full speed. The question isn't whether we'll face a resource crisis, but when and how catastrophic it will be. But what if I told you there's a place where platinum is more common than iron is on Earth? where a single small metallic asteroid contains more nickel than all the nickel reserves on our planet combined. Where water, the most precious resource for space exploration, exists in quantities that could fuel thousands of missions to Mars? Welcome to the asteroid belt, humanity's next great frontier and possibly our salvation from resource scarcity. Between Mars and Jupiter, millions of asteroids orbit the Sun, ranging from pebbles to objects larger than entire countries. These aren't just rocks. They're concentrated repositories of nearly every element on the periodic table, formed during the violent birth of our solar system 4.6 billion years ago. The numbers are so staggering they almost seem fictional. NASA estimates that the asteroid belt contains more than $700 quintillion worth of materials. To put that in perspective, that's more wealth than the entire global economy has generated in all of human history, multiplied by several million. A single metallic asteroid just 500 meters across could contain more platinum than has ever been mined on Earth. Let's talk specifics, because the details will blow your mind. Asteroid 16 Psyche, which NASA is currently sending a mission to study, is believed to be the exposed core of a failed planet. This metallic world, roughly the size of Massachusetts, likely contains $10,000 quadrillion worth of iron, nickel, and precious metals. The platinum alone could supply Earth's needs for millions of years. Near-Earth asteroids, those cosmic neighbors that pass relatively close to our planet, offer even more immediate opportunities. Asteroid Ryugu, recently visited by Japan's Hayabusa 2 mission, is what scientists call a carbonaceous chondrite. These dark asteroids are essentially flying reservoirs of water, organic compounds, and precious metals. The water content alone in some of these asteroids could support entire space colonies. But it's not just about the exotic elements. Iron and nickel, the backbone materials of industrial civilization, exist in asteroid concentrations that dwarf anything we find on Earth. A typical metallic asteroid contains 30 to 40% iron and 10 to 30% nickel. Compare that to Earth's richest iron ore deposits, which contain maybe 65% iron, and you begin to understand why asteroid mining isn't just lucrative, it's inevitable. The rare earth elements that cause so much geopolitical tension on Earth are abundant in certain types of asteroids. These materials, essential for everything from smartphone screens to military radar systems, could be extracted from space without the environmental devastation and political complications of terrestrial mining. And here's something that will change your perspective on space exploration forever. Water in space isn't just for drinking. Water can be broken down into hydrogen and oxygen, rocket fuel. Every kilogram of water extracted from an asteroid and processed in space could eliminate the need to launch that same kilogram from Earth at a cost of thousands of dollars. Suddenly, deep space exploration doesn't require carrying all your fuel from the bottom of Earth's gravity well. Think about what this means for the economics of space. Right now, it costs roughly $10,000 to $20,000 to launch every kilogram into space. But if we could mine water from asteroids and convert it to fuel, we could establish gas stations in space. Mars missions become cheaper. Lunar bases become sustainable. The outer solar system becomes accessible. Several companies are already positioning themselves as the pioneers of this new space economy. Planetary Resources, before being acquired, raised tens of millions of dollars specifically to develop asteroid mining technology. Deep Space Industries, now part of Bradford Space, was developing the first commercial asteroid prospecting missions. Even established aerospace companies like Lockheed Martin and Boeing are investing heavily in space mining technologies. But perhaps the most intriguing player is a company you might not expect, SpaceX. While Elon Musk talks publicly about Mars colonization, the economic foundation for that vision relies heavily on space-based resource extraction. You can't build a self-sustaining Mars colony by shipping everything from Earth. You need to mine asteroids, process materials in space, and build a true space-based economy. The potential economic disruption is almost impossible to fathom. Goldman Sachs has estimated that the first asteroid mining company to successfully return materials to Earth could become the world's first trillionaire. But the real wealth won't come from crashing Earth's commodity markets. It will come from building an entirely new economy in space. Now, I want to pause here and ask you something. As you're learning about these incredible possibilities, what aspects of asteroid mining fascinate you most? Is it the mind-bending wealth potential, the technology challenges, or maybe the idea that this could solve Earth's resource problems? Share your thoughts in the comments because I read every single one, and your perspectives help me understand what topics to dive deeper into in future videos. Of course, dreaming about cosmic riches is one thing. Actually going out there and mining asteroids is an engineering challenge that pushes the boundaries of human technology and ingenuity. We're not just talking about scaling up existing mining techniques. We're talking about reinventing the entire concept of resource extraction for an environment unlike anything on Earth. First, there's the small matter of getting there. Most near-Earth asteroids are still millions of kilometers away. Even the closest ones require months or years of travel time with current propulsion technology. Traditional chemical rockets, the kind we've used for decades, are simply too slow and fuel inefficient for regular cargo runs to asteroids. Enter ion propulsion, a technology that sounds like science fiction but is already being used in space missions today. Ion drives use electricity to accelerate charged particles to incredibly high speeds, providing thrust that's gentle but continuous. NASA's Dawn mission used ion propulsion to visit both the asteroid Vesta and the dwarf planet Ceres, proving that this technology can handle long-duration asteroid missions. But ion drives are just the beginning. Companies and space agencies are developing solar sails that use photon pressure from sunlight for propulsion, nuclear-powered spacecraft that could cut travel times dramatically, and even more exotic concepts like fusion rockets that could make asteroid runs as routine as international flights. Once you arrive at an asteroid, the real challenges begin. Imagine trying to mine in an environment with virtually no gravity, where careless movement could send you drifting away from your work site forever. Everything behaves differently in microgravity. Dust doesn't settle. It floats around in clouds that can jam machinery and obscure vision. Traditional drilling and digging techniques don't work when there's no gravitational force to provide stability. The solutions being developed are genuinely revolutionary. Instead of traditional mining equipment, asteroid miners are designing systems that work more like controlled explosions or focused heating. One concept involves using concentrated solar energy to heat portions of an asteroid until materials sublimate directly from solid to gas, which can then be captured and processed. Another approach uses what scientists call optical mining, essentially using powerful lasers to vaporize surface materials and collect the resulting vapors. This isn't just theoretical. Companies like TransAstra are already testing these technologies on Earth, preparing for eventual space deployment. Robotics represents perhaps the most crucial technological frontier. Human miners can't realistically work on asteroids for extended periods. The radiation exposure, the isolation, the physiological challenges of long-term microgravity, it's simply not sustainable. Instead, asteroid mining will rely on sophisticated robotic systems that can operate autonomously for months or years at a time. These aren't the simple robots we see in factories today. Asteroid mining robots need to be able to navigate complex three-dimensional environments, adapt to unexpected situations, repair themselves when components fail, and coordinate with other robots in a swarm-like network. It's artificial intelligence meets space exploration meets industrial automation. Companies like Made in Space, now part of Redwire, have already demonstrated 3D printing in zero gravity aboard the International Space Station. This technology could be scaled up to allow robots to manufacture their own replacement parts, or even build entirely new mining equipment from raw asteroid materials. But perhaps the most elegant solution being developed is something called in situ resource utilization, or ISRU. Instead of mining materials and shipping them back to Earth, ISRU involves processing asteroid resources right where you find them. Water gets split into hydrogen and oxygen. Metals get refined into pure forms. Rocky materials get processed into construction materials. NASA's Mars missions are already testing ISRU technology. The Perseverance rover carries an experiment called MOXIE that extracts oxygen from the Martian atmosphere. This same principle, scaled up and adapted for asteroid environments, could turn every asteroid into a self-contained factory and fuel depot. The technological challenges extend beyond just the mining itself. How do you maintain equipment in the harsh environment of space? How do you handle the extreme temperature swings as an asteroid rotates between sunlight and shadow? How do you deal with the constant bombardment of cosmic radiation and micrometeorites? Some of the solutions being developed sound like they belong in a science fiction novel. Self-healing materials that can repair minor damage automatically. Distributed processing systems where multiple small robots work together like a swarm of bees. Advanced materials that can withstand temperature changes of hundreds of degrees. Communication presents its own unique challenges. Earth-based mission control might be anywhere from 20 minutes to over an hour away by radio signal, depending on orbital positions. Asteroid mining operations will need to be largely autonomous, with artificial intelligence systems making split-second decisions without human input. Energy generation in deep space requires rethinking our entire approach to power systems. Solar panels become less effective the farther you get from the sun. Nuclear power sources become more attractive, but they need to be incredibly reliable since there's no possibility of easy maintenance or replacement. The cutting-edge research happening right now is genuinely mind-blowing. Engineers at companies like Honeybee Robotics are developing drilling systems that can work in zero gravity. Researchers at Colorado School of Mines are testing asteroid simulant materials to understand how different types of space rocks behave under various extraction techniques. Japan's recent Hayabusa missions have provided invaluable data about asteroid composition and behavior. When Hayabusa 2 fired a projectile into asteroid Ryugu and collected the resulting debris, it demonstrated that we can already perform basic resource extraction operations on asteroids. The samples returned to Earth are providing blueprints for future large-scale mining operations. Private companies are moving beyond theoretical research into actual hardware development. Clio Space is developing satellite systems for asteroid tracking and characterization. Bradford Space is working on small spacecraft specifically designed for asteroid reconnaissance missions. These aren't decades-away dreams. These are engineering projects with concrete timelines and funding. The European Space Agency's recent decision to redirect the Hera mission to study the asteroid Didymos, particularly after NASA's DART impact test, demonstrates that major space agencies see asteroid interaction as a critical near-term priority. Every time we send a mission to an asteroid, we're essentially conducting geological surveys for future mining operations. But what really excites engineers and entrepreneurs isn't just the technological challenge. It's the recognition that we're building the foundation technologies for humanity's expansion beyond Earth. The robots that mine asteroids will be adapted for Mars colonization. The ISRU systems that process asteroid materials will be scaled up for lunar manufacturing. The autonomous navigation systems will enable deep space exploration. However, all the engineering brilliance in the world means nothing if we can't answer some fundamental questions about law, ethics, and international cooperation. Who owns an asteroid? Can a company claim exclusive mining rights to a celestial body? What happens when multiple nations or corporations want to mine the same asteroid? These aren't hypothetical questions anymore. In 2015, the United States passed the Commercial Space Launch Competitiveness Act, which grants American companies the right to own materials they extract from asteroids, even though they can't own the asteroids themselves. Luxembourg passed similar legislation and has positioned itself as the European hub for asteroid mining companies. But international space law is based on the 1967 Outer Space Treaty, which declares that celestial bodies are the common heritage of mankind and prohibits national appropriation of space objects. How do you reconcile private ownership of extracted materials with the principle that space belongs to all humanity? The legal complexities multiply when you consider that asteroids don't respect Earth's political boundaries. An asteroid that passes near the United States today might be near China tomorrow. Whose laws apply? What if a company from one country establishes mining operations on an asteroid that another country considers strategically important? Some legal experts argue for a system similar to deep-sea mining regulations, where international bodies grant licenses and oversee operations. Others propose that asteroid mining should be regulated like Antarctica, with international cooperation and environmental protection as core principles. The environmental questions are equally complex. While asteroid mining could reduce environmental damage on Earth by eliminating the need for terrestrial mining, large-scale space operations create their own environmental challenges. Space debris is already a serious problem in Earth orbit. What happens when we have dozens or hundreds of asteroid mining operations creating additional debris? There's also the question of planetary protection. Some asteroids may contain organic compounds or even primitive life forms. Do we have an ethical obligation to study these objects thoroughly before strip mining them? How do we balance scientific discovery with economic exploitation? The geopolitical implications of asteroid mining could reshape international relations in ways we're only beginning to understand. Countries that currently derive significant economic power from mining operations, Australia's iron ore, Chile's copper, the Democratic Republic of Congo's cobalt, could see their influence diminish dramatically if asteroid materials flood global markets. Conversely, countries with advanced space technology could find themselves controlling resources that dwarf traditional earthbound reserves. This could create entirely new forms of international dependency and competition. What happens when the economic power of oil-rich nations is eclipsed by the space mining capabilities of technology-rich nations? Some analysts warn about the potential for space colonialism, where technologically advanced nations exploit space resources while leaving developing countries further behind. Others argue that abundant asteroid materials could democratize access to advanced technologies, lifting global living standards. The ethical questions extend to future generations. Do we have the right to extract materials from celestial bodies that have remained unchanged for billions of years? Are we obligated to preserve some asteroids as natural monuments or scientific reserves? There's also the question of equitable distribution. If asteroid mining generates unprecedented wealth, how should those benefits be shared? Should there be international funds similar to the United Nations' proposed mechanisms for deep-sea mining revenues? The insurance and liability issues alone are staggering to contemplate. What happens if an asteroid mining operation goes wrong and debris threatens satellites or even populated areas on Earth? Who pays for cleanup? How do you calculate insurance premiums for operations in an environment where we have limited experience and data? Some companies are already addressing these challenges proactively. Planetary Resources, during its active years, worked closely with legal experts to develop frameworks for responsible asteroid mining. Current companies in the space are engaging with international organizations to help shape future regulations rather than waiting for governments to impose restrictions. But perhaps the most important consideration isn't legal or technical, it's philosophical. Asteroid mining represents humanity's first step toward becoming a truly spacefaring civilization. The decisions we make now about how to conduct these operations will set precedents for centuries of space development. Are we approaching this as a careful, collaborative endeavor that benefits all of humanity? Or are we rushing toward a new form of resource exploitation that replicates Earth's worst environmental and social mistakes on a cosmic scale? Now I'm curious about your perspective on all of this. We've covered the incredible technical challenges and the complex legal questions, but what do you think about the broader implications? Should asteroid mining be internationally regulated, or should we let private companies and individual nations compete freely? Drop your thoughts in the comments. I love seeing different viewpoints from around the world, and your insights often give me ideas for future deep dive videos. Let me paint you a picture of what success in asteroid mining could mean for humanity's future. Imagine a world where the phrase, limited natural resources, becomes as obsolete as, the Earth is flat, or, computers will never be useful for ordinary people. Imagine technologies and possibilities that are currently impossible due to material scarcity becoming not just feasible, but commonplace. Picture orbital manufacturing facilities where the abundant metals extracted from asteroids are processed in the perfect vacuum and zero gravity of space, creating materials with properties impossible to achieve on Earth. Products manufactured without the constraints of gravity could have structural perfections and unique characteristics that revolutionize everything from electronics to construction materials. Envision permanent space colonies no longer dependent on expensive supply missions from Earth. With asteroid-derived water providing life support and fuel, with abundant metals providing construction materials, and with organic compounds from carbonaceous asteroids potentially supporting agriculture, these communities could become truly self-sustaining. Mars colonies wouldn't just be scientific outposts. They could become thriving cities supporting millions of people. The space economy that emerges could dwarf anything we've seen in human history. When the cost of materials in space drops from thousands of dollars per kilogram to essentially the cost of transportation and processing, entirely new industries become possible. Solar power satellites using abundant space-manufactured materials could beam clean energy back to Earth. Space hotels and tourism facilities could be built with materials that would be prohibitively expensive to launch from Earth. Deep space exploration would be transformed from occasional, incredibly expensive missions to routine operations. With fuel and supplies available from asteroid sources, missions to Jupiter's moons, Saturn's rings, and beyond would become economically feasible. We could establish research stations throughout the solar system, unlocking scientific discoveries that could advance human knowledge by centuries. The implications for Earth's environment could be revolutionary. Instead of strip mining mountains for copper, clear-cutting forests for rare earth elements, or poisoning groundwater for lithium extraction, we could satisfy our material needs without touching another acre of pristine wilderness. Entire ecosystems could be restored once the economic pressure for destructive mining operations disappears. Climate change mitigation technologies that are currently limited by material scarcity could be deployed at massive scales. Imagine enough rare earth elements to build wind turbines for every suitable location on Earth, or sufficient lithium to provide battery storage for global renewable energy systems. The green energy transition could accelerate from decades to years. Medical technologies could advance in ways currently unimaginable. Platinum group metals are crucial for fuel cells and certain medical devices, but their scarcity limits applications. With abundant platinum from asteroids, hydrogen fuel cell technology could replace combustion engines globally, while advanced medical implants and diagnostic equipment could become available worldwide. The democratization of advanced materials could level the global playing field in unprecedented ways. Countries that currently lack access to certain strategic materials due to geographic or political constraints could participate fully in advanced manufacturing and technology development. The artificial scarcity that creates international tensions could become a thing of the past. But the most profound change might be psychological and cultural. For the first time in human history, we would live in a world of genuine material abundance rather than managed scarcity. Economic systems built around the assumption of limited resources would need fundamental restructuring. The entire concept of wealth, based on controlling scarce resources, could be revolutionized. Educational systems would need to prepare students for careers that don't exist yet. Space-based resource extraction engineer, orbital manufacturing specialist, asteroid logistics coordinator. These job titles sound like science fiction, but they could be as common as software developer or renewable energy technician within a generation or two. The cultural impact of seeing Earth from space has been well documented among astronauts. The overview effect, that provides a cosmic perspective on human unity and Earth's fragility. When space-based work becomes routine for thousands or millions of people, this expanded perspective could become a common human experience rather than the privilege of a few explorers. International cooperation could be strengthened by shared space-based economic interests. When countries have significant investments in asteroid mining operations and space-based manufacturing, the incentive to maintain peaceful relations increases. War becomes not just morally questionable but economically irrational when it threatens space-based assets that benefit everyone. The timeline for these transformations is closer than most people imagine. Current projections suggest that the first commercial asteroid mining operations could begin within the next 10 to 15 years. The first significant quantities of space-derived materials could reach Earth markets within 20 to 30 years. Within 50 years, space-based resource extraction could be a routine part of the global economy. Children being born today could live to see a world where scarcity of physical materials is a historical curiosity, where space colonies are thriving communities, and where humanity's expansion throughout the solar system is well underway. The generation currently in college could be the architects and engineers of this new space-based civilization. Private companies are already investing billions of dollars in the foundational technologies. Government space agencies are developing the scientific understanding and regulatory frameworks. International organizations are beginning to address the legal and ethical questions. The convergence of these efforts is creating momentum that seems unstoppable. But perhaps the most exciting aspect of this future isn't the technology or the economics. It's the sense of renewed purpose and adventure it could provide humanity. For the first time in generations, we're facing challenges that require the best of human ingenuity, cooperation, and exploration. The space age that began with the Apollo missions and then seemed to stagnate could enter a new golden age driven by economic opportunity rather than just national pride. The young people watching this video could be the ones who make this vision reality. The decisions being made in corporate boardrooms, university laboratories, and government offices today will determine whether this transformation happens smoothly and beneficially, or whether it's delayed by short-sighted thinking and unnecessary conflicts. Every major technological revolution in human history, agriculture, industrialization, the information age, has been driven by visionaries who could see beyond the limitations of their current circumstances. Asteroid mining represents the next revolution, and it's beginning now, with the choices we make and the support we provide to the pioneers pushing these boundaries. The question isn't whether this future will arrive, but how quickly, and whether humanity will be wise enough to manage this transition in ways that benefit everyone rather than creating new forms of inequality and environmental destruction. As we reach the end of this journey through the cosmos of asteroid mining, I want you to consider something profound. We've explored together a future that seemed impossible just decades ago, but now appears inevitable. We've seen how the combination of human ingenuity, economic incentive, and technological capability is converging to solve one of civilization's greatest challenges: the limitation of natural resources. The implications stretch far beyond mining and manufacturing. We're talking about humanity's graduation from a single-planet species to a true spacefaring civilization. The children being born today might be the first generation to grow up in a world where space-based work is routine, where lunar cities exist, where Mars colonies are thriving, and where the vast wealth of the solar system is available to support human prosperity and exploration. The challenges we've discussed, the engineering complexities, the legal frameworks, the international cooperation required, are exactly the kinds of problems that human civilization excels at solving when we're motivated by both necessity and opportunity. The history of technological progress shows that what seems impossible becomes inevitable with remarkable speed once the foundational pieces fall into place. Right now, in laboratories and corporate offices around the world, engineers and entrepreneurs are solving the technical problems of asteroid mining. In government offices and international organizations, lawyers and diplomats are crafting the regulatory frameworks that will govern space resource extraction. In universities and research institutions, scientists are studying asteroid composition and developing the theoretical foundations for large-scale space operations. This isn't a distant dream. It's an emerging reality. The first asteroid mining companies are already raising investment capital. Space agencies are launching missions to study and interact with asteroids. The legal frameworks are being established. The international cooperation mechanisms are being developed. But what makes this moment truly special is that you, yes you, watching this video, are witnessing the beginning of humanity's next great adventure. Your generation might be remembered as the one that took the crucial first steps beyond Earth, not just for exploration, but for the practical business of building a space-based civilization. The future we've explored today doesn't depend on breakthrough physics or revolutionary discoveries. It depends on scaling up technologies we already understand, solving engineering challenges we already know how to approach, and making political and economic decisions we're already capable of making wisely. Every time you hear about a successful space mission, every time a private company announces progress toward asteroid mining capabilities, every time an international agreement addresses space resource rights, you're witnessing another piece falling into place in humanity's expansion beyond Earth. The transformation we've discussed will happen gradually, then suddenly. Just as the internet went from a curiosity used by researchers to an essential part of daily life for billions of people in barely 2 decades, asteroid mining could go from experimental missions to routine operations faster than most people expect. Your role in this future might be as an engineer developing space-based technologies, as an entrepreneur building space economy businesses, as a policymaker crafting the regulations that will govern this new frontier, or simply as a citizen supporting the bold decisions needed to make this vision reality. But regardless of your specific role, you're part of the generation that will determine whether humanity successfully makes this transition to space-based resource abundance, or whether we remain trapped by the artificial scarcity that has limited human potential throughout history. The cosmos is vast, ancient, and filled with more wealth than our planet-bound ancestors could have imagined. The question isn't whether that wealth exists. We know it does. The question is whether we have the wisdom, cooperation, and determination to claim our inheritance among the stars. This is our moment. This is our choice. This is our future, waiting to be built. What role will you play in making it reality? Share your thoughts, your concerns, your excitement, your questions in the comments below. Whether you're a student wondering about career paths, an investor curious about opportunities, or simply someone fascinated by humanity's potential, I want to hear from you. And if this vision of the future excites you as much as it excites me, share this video with someone who needs to understand what's coming. Subscribe for more explorations of the technologies and possibilities that will shape our future. Hit that notification bell so you don't miss any updates on humanity's greatest adventure. The future is being written right now, in real time, by real people working on real projects. The only question is whether you'll help write it, or just read about it in history books. Thank you for joining me on this journey to the asteroids and back. The universe is vast, the opportunities are limitless, and the adventure has only just begun.